on Friday, we didn't quite get through the whole deck of slides that I had put together. I had several work numerical problems in there, and yeah, there was that. So I'm going to go through, hit the rest of those, and then dig into chapter 24 a little bit. Chapter 24 is on electromagnetic radiation, like light, X-rays, gamma rays, radio waves, all that kind of good stuff. So, and then I think that is, I'd have to look. Yeah, where is the cutoff for test 2 material? There we go. It's like, I thought I actually printed off a syllabus to keep with me. But it should say on here, yes, test 2 is chapters 22, 23, and 24. So we're wrapping up chapter 23 today, and we'll start into chapter 24 a little bit. Okay, so we've been talking about electricity, we've been talking about magnetism. One of the things that most people will appreciate is electrical safety. How to keep the electricity from killing you, which is a really good thing. So there's 2 main things that make electricity kind of dangerous. Not just kind of. It's dangerous. I don't need to qualify. It can be dangerous. One is the thermal hazard, and the other is the shock hazard. So what do you think I mean by thermal hazard? The heat. That you have resistance. If the electricity is trying to go through you, you will heat up. You can cook yourself. In fact, that's how a lot of electrical accidents happen. People go through and the electricity, try to think how far, I need to take a step back, whether I need 1, 2, 3 steps back. I mentioned early on that our bodies run on electricity. Nerve impulses are electricity. They are a flow of charge from one spot to another, from one end of a nerve cell to another, then across the gap to the next nerve cell, to the next nerve cell, to the next nerve cell. That flow of charge is electricity. It's current. Well, those nerve cells tell your muscles to go through and contract. Other muscles go through saying, open the hand. Other muscles say, close the hand. Open the hand, close the hand. If all of those are firing at the exact same time because of some electrical shock going through your body, which is generally stronger? Your ability to close your hand or open your hand? Close. So if you're reaching in and touching something that's electrical, both are trying to happen at the same time, but the close your hand is generally stronger. You will grip onto that thing, that wire, and you won't be able to let go. You won't be able to let go. The electricity will be going through and firing those nerves and contracting those muscles for you, regardless of whatever your brain wants to have happen. We were actually... Maybe this is a good idea, maybe it's not. I don't know. We didn't actually do it. But we were actually thinking with Music Fest a couple weeks ago. We had a little recruiting booth, and we were thinking like, as biomedical science and chemistry, we were like, wouldn't it be fun if we could go through and hook up those little TENS sensors, the little electroshock pads, and go through and shock people's muscles and make them like play a piano or a flute or something. All they had to do was hold on to it, and then we, run it electronically. I thought that was the coolest thing. I thought that'd be like really cool. And some of the biology professors were like, yeah, maybe. We'll see. And then we didn't do it. So Maybe it hurts more than I think it does. I don't know. But you can do it. There is a biological way to go through and make that actually happen. But when we have electrical shocks, we go through and, our muscles are going to contract whether we want them to or not. In fact, most electricians, whenever they turn on the main power to a building or something like that, usually they do it in pairs. One actually goes through and has all the protective equipment, and another one's usually back behind that person with something non-conductive to pry them off the electrical panel in case they happen to get shocked because something was done wrong. It's a real thing. But as the diagram here shows, this person is literally just acting like a resistor. Some of that electricity is going, through his arms to the pipe that's connected to the ground. That's the path of least resistance. But there's also a parallel path where it's going down through his leg and also acting like a ground. And that happens enough resistance, enough current, and for long enough, you can cook. I was going to say I could tell some really horrifying stories, but let's not do that today. At least not on the video that's going to go up on YouTube. Because I grew up on a farm. I saw some stuff. So how do we prevent such a thing from actually happening? Also shock hazards. So even if you're not like and cooking yourself, even if you go through and you just brush against something, there is something called a shock hazard that can happen from very short periods of electrical contact. What do you think a shock hazard does? Well, let me ask maybe a different way. So many of the buildings on campus have those AED systems. What's an AED do?
It shocks the heart.
Shocks the heart. And what's shocking the heart do? It basically stops it and lets it reset. So electrical shocks can stop your heart. They can go through, your heart's hitting those electrical beats, the electrical signal saying beat, 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 beat. And electrical shock comes in and goes, hey, stop it. And you can absolutely stop your heart. The whole idea behind an AED is that then you have it where it can get it started again too. Yay. But if you're having a heart attack maybe actually a heart attack probably wouldn't do much good. But if you're having some sort of heart arrhythmia or maybe something like that, maybe an AED could actually help. So we have long-term exposures will cook you. Short-terms can do things like stop your heart. How do we protect against these? Well, one is a plain old circuit breaker. Yep. And I think we talked about circuit breakers last semester. I'm pretty sure we talked about circuit breakers last semester, didn't we? Yeah. So you have the two different metals inside the circuit breaker. Yeah, just draw a circuit breaker real quick. Insert page. Insert. So a circuit breaker, you have a bar of metal. You have a piece of metal that's of one type. You have a piece of metal that is of another type, and some sort of spring. I don't know, I'll just draw the spring up here, pushing down. Well, as these two metals heat, they have different thermal expansion coefficients. So as it heats up, what ends up happening is the blue expands more and the purple expands less, and it'll expand over until that point falls into that notch, at which point that bar will fall down and the notch will keep it from resetting. The spring's pushing it down. So even if the metal cools and tries to straighten back out, that notch will say, no, hold. Wait until the human comes through and manually resets you. There are automatic resetting circuit breakers, but usually they're for like big industrial type things, not for household kind of use. But yeah, when you trip a circuit breaker, I'll just trip one up here real quick. So, ooh, no, that's, drat, I can't do that one. I could trip that one, but it's going to kill my Chromecast. But circuit breakers are usually in large. There's also ones that are built into the outlets. And those are the kinds that we're going to kind of focus on a little bit more today. But this is old-fashioned circuit breaker. Old-fashioned circuit breaker. But what's the problem with an old-fashioned circuit breaker? I mean, why is this maybe not the best way to keep you from killing yourself from an electrical shock? It's not fast. It has to heat up. It has to heat up enough for two different metals to start expanding at noticeably different rates and moving over. And it's good for not burning your house down. Good for not burning your house down. Not so good for keeping you alive. So how do we do it better? Well, there is something called a ground fault circuit interrupter, GFCI. Lately, I've just seen them called GFI, I think, outlets. They dropped the C. I'm not really sure why, but someone decided. So these U.S. electrical code, if you have an outlet within so many feet of a water source, you have to have one of these. So the water source is a nice electrical conductor to the ground. So if I went through and touched a live outlet over here, I'd be foolish. But if I touched it, I have rubber-soled shoes on. I'd probably get a shock, but probably not a deadly shock. But if I had something in water and I touched that outlet, I would probably be toast. If it weren't a GFCI outlet. Now, you may also be going through and saying, hey, and I'll even take a picture. Camera, picture. Okay. So we have our GFCI outlet here. I'll crop it in a little bit. So our GFCI outlet has a test and reset button on it. That's one way that you can always tell if it's a GFCI. But I said any outlet within so many feet. I mean, this outlet is within so many feet of that sink. But if you look along the wall, you have outlets that are a lot closer than that don't have that little button in the middle. Those actually have the circuit breakers that have the GFCI built into them over here. So if I make this much smaller and kind of put it out of the way, make it really small. Tiny, tiny. And I use the camera over here. I have and do some cropping on this. I have, that's a little big. Make this smaller and smaller. So here I have the GFCI actually built into the circuit breaker. It shows up better if I do it in red. So that's actually built into the circuit breaker. And like almost all of the outlets in this room are close to a water source. They all are basically GFCI. If you look inside that circuit, that breaker box, like those little yellow buttons are on almost every circuit because almost everything in here is within the prescribed number of feet of a water source. So, okay, we've established that they're required by law. We've established, I've told you that they will keep you from dying in electrical shock. How does it work? I mean, obviously it doesn't require heating like the traditional circuit breakers. What it does is it works off induction. So that same kind of wireless charging, current going through this loop will make a magnetic field over here, which will make a current in that loop that tries to resist it. All that kind of good stuff. Yeah. So we have, in this case, let's zoom in here a little bit. We have in our GFCI outlet a sensing coil. So that coil doesn't have anything applied to it. It's just there as like a radio antenna to pick up any kind of currents that it might be able to pick up. And we run our 2 wires in and out through an iron ring. So if I look at the arrows going this way, and I use my right hand rule, so current is going that way, my thumb is going in the direction of the red arrow, I would have magnetic field going counterclockwise, wouldn't I? If I look at the current coming back, it would be going the other way. I would have current going, or magnetic field going clockwise. Assuming that the device that's running on the electricity isn't using a huge amount of electricity, the forward and reverse should be pretty equal, shouldn't they? If those are pretty equal, then the clockwise and counterclockwise magnetic fields should also be equal but opposite. If you're equal but opposite, will you have really much current that's being picked up by the sensing coils? No, they're being canceled out. But But if you have a short circuit and some of the return current is going through you and not back through that iron ring, are they going to be equal and opposite anymore? No. Out is towards you is still going. Coming back, not so much. It's going through you to get to the ground, not back through the wires to try to get through the ground. That's how a ground fault interrupter works. It's also, because it's not relying on things to get hot, it's incredibly fast. Milliseconds fast, usually, for most of these. And usually that's enough to prevent you from having serious, health effects from the electricity if it can shut it off quickly enough. Bless you. But that's a ground fault circuit interrupter. It says they generally trip at about 5 milliamps of leakage. So when the forward and reverse induced currents are more than 5 milliamps different, that's usually enough to go through and trip the circuit. But 5 milliamps generally is not enough to stop your heart. Generally, 5 milliamps should not cook you in any appreciable way. Just like we saw with Van de Graaff generators. It's not the voltage that tends to kill. Oh, wow, I have the hiccups. At some point I'm going to get past them. But as we saw from the Van de Graaff generator, you can be shocked by, 500,000 volts of voltage. As long as it's really low current, it hurts, but it's not going to kill you. Same thing here. These are designed to trip at very low currents, so that it's going to trip before it actually has a chance to kill you. But yeah, this is how we go through and try to make electrical things safer. People that go through and disable, make their electrical safety things not work properly are foolish. I've known people that have done that. Like, this circuit breaker keeps tripping. I want to tape it into the on position. I was like, no, don't. You're going to burn your house down. There's a reason why they trip. I will also say, if you have an older house and you have trouble with these tripping, do try replacing the either the circuit breaker or the GFCI outlet. Sometimes if they've been tripped a lot, they start getting a little weak. They start tripping easier as they've been tripped, not harder. So if it is tripping easy, don't just assume that it's like, it's just being ridiculous, I'm going to tape it open. Replace it. If it still is tripping, then you probably have a problem that you need to have fixed. If replacing it fixes it, then it's fixed anyway, and you're still safe without having it taped into an on position or something like that.
How easy are those to replace?
If you with like that outlet, I'd find the circuit breaker. It would be 5 to 6 screws to take out and put back in, and you can have it replaced. But you want to make sure that it's completely de-energized. The electricity's cut off to it beforehand. Even though I've seen people do them hot, that's generally not a great thing to do. That's kind of one of those, if you're a professional, you know how to get away with some things. But for hobbyists, homeowners, I wouldn't try it. I would just kill the power to the circuit and then replace it when it's de-energized. But yeah, I have seen people do them hot, but generally not a good idea. Okay, questions on GFCIs? Do they seem okay? Okay, so Inductance, mutual inductance. This is where we get into our wireless charging. So we have the charging coil, and then we have the thing being charged. The biggest thing between these two is there is a factor of M. Now, I don't tend to ever ask questions about like what's M, but M takes into account all the things that make charging not so efficient. So I think I asked about wireless charging before. If I remember right, I saw a couple of hands. Is there an optimal placement of your phone or smartwatch on the charging pad? Yeah, if you get it a little bit off center, it doesn't charge as well. That's the M factor. That's one of the things that it takes into account. If they're farther apart, so you have a really thick phone case, charging's not going to be as efficient. That's another thing that's wrapped up into that capital M. But those are alignment, those are distance issues. Anything that's going to cause the charging to be less efficient is going to get wrapped up basically in that M, because there's really nothing else in the equation to do it. There really isn't. Self-inductance. Energy stored in an inductor. RL circuits. I'm only going to talk about these very briefly, but mainly to show that there are parallels between what we had with inductors and what we have with capacitors. So we talked a lot about capacitors, so I don't want to completely just my way through the inductance. But if you notice, the energy stored in an inductor and the energy stored in the capacitor are very similar. They're very similar. Now, when we stored a charge or stored energy in a capacitor, what form did that energy take? I mean, it was voltage, but what caused the voltage?
The difference, because they were close.
The difference of charges. So we have stored charges, pluses and minuses, that's going through and storing energy in the capacitor. What's storing the energy in an inductor? In a coil of wire that has electricity running through it. What's storing energy there? It's the magnetic fields. So that magnetic field is being created by the electricity running through there. If the electricity were simply to stop, as that magnetic field disappeared, it would be going through and creating some electricity. So one is being a storage of charge to store the energy. The other is a storage of magnetic field to store the energy. But the equations look really, really, really similar between those two. The current at any time, or the voltage at any time, does that next line of equations, do those look pretty similar to each other? Yeah. And the next one. And the next one. Yeah. They all have these, the tau down here on both of these, they're both, the tau is called a time constant. Yeah, it looks like the symbol for torque, and it is the same symbol for torque. But in electricity, we call it time constant. But yeah, there's a lot of similarities. There's a lot of similarities. I am not going to have you go through and do calculations with any of those. There might be one of those that sneaks in on the homework, maybe, I don't The L is the inductance, kind of like the capacitance of a capacitor. I is just current. But yeah, I can't remember if I put one of those on the homework or not, but there might be. But again, you can probably see me kind of being maybe a little dismissive on this. I don't do a lot of these kind of calculations because if you're going into chemistry, if you're going into medicine, dentistry, you're not going to use these equations all that often. The idea of inductance, the concept of inductance is good, but doing a lot of calculations with it, nah. It just doesn't serve a lot of purpose for us. Electrical engineers would eat this up, but we're not electrical engineers, so we can save ourselves a little bit of that headache that they would have to endure. Okay, does this seem okay? Okay, so that's the end of chapter 23, and now we're jumping into chapter 24. Electromagnetic waves, and oh, hey, we've done this page. Actually, we've done all those pages. Let me clean that up. Okay, so electromagnetism, sometimes referred to as simply EM radiation, is described fairly thoroughly by four equations that were discovered, put together by James Clerk Maxwell. They're called Maxwell's equations. Now, if this was the calculus-based version of the course, I would be going nuts. I would be going absolutely bonkers on Maxwell's equations, because Maxwell's equations can calculate crazy kind of things from just simple data. But it needs calculus. Not just Calc 1. It's kind of Calc 2 level, if not Calc 3 level. Yeah, I know. So we're going to go through a very descriptive version of Maxwell's equations, which describe the heart of what you would find if you could actually do the calculations. We just don't have the math as a prerequisite for this course to be able to go through them. But if you hear me, sounding kind of like I'm pining for, it'd be great to do a calculation on this. It would be, but it would also take a lot more calculus. So not going there right now. So electric field lines. That's one of the cool things that Maxwell's equations will let us do. It'll actually let us go through and calculate electric field lines in really complex systems. But they originate on positive charges. They terminate. They go into negative charges. We've seen that before. That's not new. We're just putting it into a broader framework here. Electric field is defined as force per unit charge on a test charge. That's exactly how we defined it in chapter 19. The strength of the force is related to the electric constant, the permittivity of free space. Yeah, that was one of those terms that showed up on the equation sheet last time. Didn't spend a lot of time on it, but it is out there. We'll spend a little bit more time talking about epsilon naught and mu naught as we talk about Maxwell's equations. And Coulomb's law has a kind of more focused version of it that's called Gauss's law for electricity. What was Coulomb's law? We talked about that in class. Does anyone remember which one we called Coulomb's law? r squared. That was the Coulomb force. So we have two different charges. They're oppositely charged. They're going to attract. Same charge. They're going to repel. But that's the force between them. So yeah, nothing really new here. Nothing really new here. Magnetic field lines. Also, nothing terribly new here either. They're continuous. They go from the north, out of the north and into the south. No magnetic monopoles are known to exist. The strength of the magnetic force is related to our mu naught. So I said we'd spend more time with epsilon naught and mu naught as we start talking about electromagnetism. Hints of that coming. And then we have Gauss's law for magnetism as the equation form that kind of summarizes what we get into here. A changing magnetic field induces an EMF. If there's an EMF, then there's an electric field. And the direction of the EMF opposes the change. So we're opposing the change. That's Faraday's law. That's Lenz's law. That's what we're going to be doing tomorrow in lab. Is we're actually going to be playing with Faraday's law a little bit, actually measuring these induced currents using really strong magnets glued to dowel rods, glued to wooden sticks. So, but we're going to play with them a little bit. We're going to see what happens and quantify a little bit about what's going on with that. But yeah, Faraday's law and Lenz's law is just a subsection out of Faraday's law. Magnetic fields generated by moving charges or changing electric fields. So we can have electromagnets. We can mix solenoids. That works. We can also go through and have a varying, like AC current. That's changing our electric field. That will also create magnetic fields as well. And that's another source of magnetism that can actually happen. So all of that is really just kind of a recap of what we've done over the last 3 chapters. I mean, really, it's the heart of what we've been trying to dig into over about the last 3 chapters. And as we look at mu naught, epsilon naught, we can actually start to unify it a little bit more. Spencer, what do you think the C stands for there? No, that would be a capital C. I'll give you a hint. It's the same C as E equals mc squared. Jacob's smiling.
I have no idea.
Isaac, I think, actually knows. Isaac, help us out.
Speed of light.
Speed of light. So, all of a sudden, we're taking these ideas that we had from electricity and from magnetism. We pull out some of those constants, and they're related to the speed of light. This is one of the things that made Maxwell really stand out from his colleagues at the time. There were a lot of people working on electricity. He was by no means the only one. But one of the first things he did was came up with these mathematical relations and started to realize that the speed of light was tied to electrical and magnetic properties as well. We're going to find out that light is actually a series of electrical and magnetic fields. it makes sense once we get through this. You'll be able to look back and be like, of course that would be the relationship. Right now it's just like, okay, if you tell me. And I get that. But this is kind of one of those things like E equals mc squared, that Einstein equation that takes matter and converts it into energy, atomic bombs and things like that. This is one of those things that was a revelation at the time and really opened people's eyes to the fact that these weren't so cubbyholed in different areas of study as they thought they were up to that point. They realized this is all a unification of forces. Things like electromagnets and X-rays have something inherently, fundamentally in common between them. And that's kind of what we're going to be digging into in chapter 24. So, electromagnetic waves. So, if I have KZUM, the radio station that's just across the street here, I think that's the call letters for it. Yeah, they have an antenna. They broadcast radio waves. We have a Wi-Fi access point. It has a much smaller antenna, but it also broadcasts radio waves. How do radio waves actually happen? Well, to create a radio wave, we have a separation of charge based upon a voltage that's applied. But as that voltage is applied, we go from having no charge to some charge to full charge and back. It grows, it sinks. It grows, it sinks. But as it's growing, that electric field will be growing as well. As we put more charge on the extreme ends of that antenna, we're going to have a greater electric field that builds because of that separation of charge. Bless you. As that AC current starts going back down, I mean, eventually it crosses 0 volts. 0 volts, you wouldn't expect to have any charge separated. This is all going to be uniform. But it starts going back down. That electric field starts shrinking as the magnitude of the charge separation decreases as well. Eventually, AC current, it was positive, now it's going negative. It's pushing the charges in opposite directions. So now the electric field's pointing the other direction because the positives are down below and the negatives are up high. It goes back and forth and back and forth and back and forth. It creates a sinusoidal wave that propagates out away from this antenna at the speed of light. At the speed of light. Now, as we have that electric field, as we're going through and moving the charges to those extremes of the antenna, you have a current, don't you? Moving charge is a current. If I put my thumb in the direction of that current and I wrap my fingers, will I not create a magnetic field? Right-hand rule 2. Right-hand rule 2. So, as those charges are being moved, I'm increasing the electric field, but the moving of the charges themselves creates a current. And that current creates a magnetic field. That magnetic field will be 90 degrees away. It will be at a 90 degrees offset from the electric field. So if the electric field is going up and down along the antenna, the magnetic field is curving around. It's going side to side. It's perpendicular. So, out of curiosity, how many people have seen a diagram of electromagnetic radiation that kind of shows this, where you have the electric field going one way and the other one going the other way? I mean, it's a pretty common description. A lot of times you don't get a good explanation as to why it would ever do that. But we've actually built up enough that we can actually explain that. This part is coming from right hand rule 2 as the charges are actually moving. This is just the charges moving, causing more and more electric field, or less as they dissipate and start going the other direction. But yeah, the other one's just right hand rule 2. But there will be, part of the reason we use our right hand, thumbs in one direction, fingers in the other, those will be 90 degrees from each other. And yeah, we're going to end up with this kind of electromagnetic radiation. Now, I'm out of time today, but on Wednesday, we'll actually jump into electromagnetic spectrum. We'll talk about visible light, microwaves, all these other kind of good things. We'll start talking about that on Wednesday. And probably we'll wrap up chapter 24 on Wednesday as well. Okay, I'm going to go ahead and call it there for the day. Have a good rest of your day, and we will catch you on the flip side.